Content in this presentation is covered on pages 170 through 176 of your textbook, and it's meant to help you achieve learning objective number 29, which is to describe the Bergeron process and explain how it differs from the collision coalescence process. Be sure to skim these pages before watching the video. Also, read the chapter carefully before attempting the online quizzes. If all clouds contain water, why do some produce precipitation while others drift placidly by? This seemingly simple question perplexed meteorologists for many years. Typical cloud droplets are minuscule. They're, 2/100ths of a millimeter in diameter. So this is another blurry diagram, but you get the idea from it that a cloud droplet is very tiny compared to other moisture droplets in the sky. So to compare the size of a cloud droplet, cloud droplets are 20 micrometers. The average human hair is about 75 micrometers. So cloud droplets are smaller than the thickness of your hair by about 4 times. Because of their small size, cloud droplets fall in still air at incredibly slow rates. An average cloud droplet falling from a cloud base at 3,000 feet would require several hours to reach the ground. However, it would never really finish its journey. Instead, the cloud droplet would evaporate before it fell even a few meters from the cloud base into unsaturated air below it. How large does a cloud droplet grow in order to fall as precipitation? A typical raindrop has a diameter of about 2 millimeters. Though it's 100 times that of the average cloud droplet. However, the volume of a typical raindrop is 1 million times that of a cloud droplet. So for precipitation to form, cloud droplets have to grow in volume by roughly 1 million times. You need 1 million times as much water. You might suspect that additional condensation creates drops large enough to survive the descent to the surface. However, clouds consist of many billions of tiny cloud droplets that all compete for the available water. So condensation provides an inefficient means of forming raindrops. 2 processes are responsible for the formation of precipitation: the Bergeron process and the collision coalescence process. The Bergeron process is named for its discoverer, Tor Bergeron. It generates much of the precipitation in the middle and high latitudes. The mechanism behind it operates using 2 important properties of water: the fact that we have supercooled water and the fact that the cloud is supersaturated. So supercooled water, let's tackle that one first. The Bergeron process only operates in clouds that are considered to be cold. So this is a cold cloud process. And that's temperatures below 0 degrees C, where liquid cloud droplets and ice crystals can coexist. Contrary to what you might expect, cloud droplets do not usually freeze at 0 degrees C. Because this process occurs high in the atmosphere, where atmospheric pressure is much lower than it is at the surface, and because water droplets in clouds are completely suspended in the air, water doesn't freeze until it reaches a temperature much lower than 0 degrees, about 40 degrees, minus 40 degrees. And that's both minus 40 C and F. Remember that those scales cross at that cold end of the thermometer. Liquid water at temperatures below 0 is therefore known as supercooled water. And in the atmosphere, supercooled droplets don't freeze until they contact some solid particle. And in a cloud that has both ice and supercooled droplets, that solid particle is going to be a hexagonal ice crystal. That term hexagonal is used because the water freezes in the free atmosphere. It's free to grow in its purest crystal form, and that atomic structure is tiny little hexagons. When you see ice like this in a big cold cloud, we call those freezing nuclei, and they're very sparse in the atmosphere. They don't generally form until the air temperature is about 15 degrees below 0 centigrade. So at temperatures between 0 and minus 15, most clouds consist only of supercooled water droplets. Between minus 15 and minus 40, most clouds consist of supercooled droplets that coexist with ice crystals. And at temperatures colder than minus 40, clouds are composed entirely of ice crystals, and they start to get that wispy look to them. For example, the tops of towering cumulonimbus clouds, like the one in this diagram here, have those wispy high-altitude cirrus clouds. Those are all the ice crystals from the top part of the cloud. Another important property of water, that was supercooling. This is about saturation vapor pressure, and it's a little trickier to understand. But saturation vapor pressure around an ice crystal is lower than it would be around a water droplet. So stated another way, when the air surrounding a water droplet reaches 100% relative humidity, it's saturated, it is much more saturated than the air around a nearby ice crystal. I think table 5.3 in your book shows you that at minus 10 degrees C, when the relative humidity is 100% with respect to water, the relative humidity with respect to ice is about 110%. Right? So that's just because we have lower saturation vapor pressures around solid water than we do around liquid water, because the ice crystals are solid, so individual ice molecules are held together more tightly than they would be in a liquid droplet. Just easier to pry those H2O molecules out of a liquid droplet. So for the same reason, water vapor molecules evaporate from water droplets at a faster rate than they do from ice crystals at any single temperature. I know that's a lot to swallow. So it should be a small section of the text if you want to read up about the Bergeron process. But get that information from your book, and we'll talk about it in class too. When ice crystals and supercooled water droplets coexist, conditions are ideal for creating precipitation. Because freezing nuclei are sparse, cold clouds consist of relatively few ice crystals surrounded by much higher concentration of liquid droplets. Since the air is supersaturated with respect to those few ice crystals, the ice crystals collect water molecules by the process of deposition. So that in turn lowers the overall relative humidity of the air. In response, the surrounding water droplets will begin to evaporate to replenish the lost water vapor. So the growth of ice crystals is fed by the continued evaporation and shrinkage of the liquid droplets. It's a positive feedback. So when the ice crystals become sufficiently large, they begin to fall. Air movement will sometimes break them up into smaller fragments. But the fragments serve as freezing nuclei for other liquid droplets. So it's kind of a chain reaction. And that produces many snow crystals, which may join together into snowflakes. The Bergeron process can produce precipitation throughout the year in the middle latitudes, provided that at least a portion of the cloud is cold enough. So it has to be a minimum of minus 15 degrees C to generate ice crystals. It could be colder than that. The type of precipitation, as we'll see in another lecture, whether you get snow, sleet, rain, or freezing rain on the ground, depends on the temperature profile in the lower few kilometers of the atmosphere. When the surface temperature is greater than 4 degrees C, snowflakes usually melt before they reach the ground and continue the descent as rain. Even on a hot summer day, a heavy rainfall may have begun as a snowstorm high in the clouds overhead. During a middle latitude winter, even low clouds are cold enough to trigger precipitation via the Bergeron process. So Bergeron is the cold process. Collision coalescence is the warm cloud process. And it's the dominant process for clouds with tops that are warmer than minus 15 degrees C. The collision, I wish I could stop saying that. The collision coalescence process involves multiple collisions of tiny cloud droplets that stick together. They coalesce to form raindrops large enough to reach the ground before evaporating. One of the requirements for the formation of raindrops by the collision coalescence process is the presence of larger than average cloud droplets. Research shows that clouds made entirely of liquid droplets usually contain some droplets that are larger than 20 micrometers or 2/100ths of a millimeter. These large droplets may form when giant condensation nuclei are present, or when hygroscopic particles like sea salts are carried by updrafts into the atmosphere. Hygroscopic particles begin to collect water vapor at relative humidities below 100%. And when large cloud droplets are intermixed with numerous smaller droplets, the conditions are ideal for making precipitation. The maximum speed at which an object falls is called its terminal velocity, and that occurs when the air resistance equals the gravitational pull on the object. Because large droplets have a smaller ratio of surface area compared to their weight, they fall faster than small droplets. Because friction operates on the surface area of the droplet, the particles with higher ratios of surface area to volume experience more friction and therefore fall at slower terminal velocities. The larger droplets fall through the cloud faster, colliding with smaller, slower droplets, and they coalesce. They become larger in the process and fall even more rapidly, or rise more slowly in an updraft. That increases the chances of collision and the rate of growth. So after a million or so cloud droplets coalesce, they form a raindrop, and that's large enough to fall to the surface without evaporating. Because of the huge number of collisions required for growth to raindrop size, clouds that have great vertical thicknesses and contain large cloud droplets have the best chance of producing precipitation. Updrafts associated with unstable air also aid this process because the droplets can traverse the cloud repeatedly. So they jumble around in there like popcorn in a popcorn popper. And that results in more collisions. As raindrops grow in size, their fall velocity increases. And that in turn increases the frictional resistance to the air, which causes the drop's bottom to flatten out. As a drop approaches 4 millimeters in diameter, it starts to develop a depression like the one shown here. Raindrops can grow to a maximum of about 5 millimeters, 2 inches, when they fall at the rate of 33 kilometers or about 20 miles per hour. At that size, the water's surface tension, which holds the drop together, is surpassed by the frictional drag of the air. And the depression grows really rapidly, almost explosively, forming a donut-like ring that immediately breaks apart. And the resulting breakup of a large raindrop produces numerous smaller drops that begin the task of sweeping up cloud droplets all over again. Use the content here and on the Canvas site, as well as outside internet sources you might know about, to verify that you can formulate the right answers to these questions. If you're comfortable answering these questions, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.